Greetings to all. I am Parth Shah, pursuing Masters in Construction Engineering and Management at CEPT University. This video presents the work carried out as a part of our Studio 3 titled Integrated Construction Practices. The focus of the studio is to bridge theoretical learning with real-world project execution by integrating two powerful approaches, which is BIM and Lean Construction. The studio allows us to understand how multidisciplinary coordination, detailed modeling, structured planning, and continuous improvement principles shape the execution of a modern construction project. Through BIM, we'll learn how digital models enhance clarity, reduces rework, and support informed decision making across all stages of the project. Bringing these approaches together helps us develop a holistic understanding of how complex projects are planned, coordinated, monitored, and delivered in today's industry. Moving on with the project brief. As a part of our studio, a real life project has been taken up, which is High Rise Commercial Tower. It is a 3 basement G plus 29-story commercial tower located in the prime business district of Gift City. It has been envisioned as a modern workplace offering premium office spaces supported by efficient planning, contemporary amenities, and sustainability driven design principles. The development occupies approximately 5,970 square meters of land and comprises a built-up area of over 66,000 square meters. The overall investment is around 415 crores with an estimated construction cost of around 160 crores. The work is being executed under an item rate contract and the construction timeline extends from November 2023 to July 2027. The location of the project is one of its strongest attributes. Situated within Gift City, a planned financial and technological hub, the site benefits from excellent regional connectivity. It is in close proximity to the airport, metro, major road, and surrounding commercial and institutional infrastructure. The project falls within the DTA zone, which supports large-scale commercial development and encourages organized urban growth. The key objectives of the development are to deliver high-performance commercial tower, ensure efficient and flexible workspaces, integrate modern services and building systems, uphold sustainability considerations, and maintain stringent safety standards throughout the project lifecycle. For our studio, the assigned scope includes one basement level and 16th floor. Within our group, responsibilities were divided to simulate a real-life project environment where I had taken up the responsibility of structural and plumbing consultant. Other consultants were distributed among the team members. Thus, therefore, this slide establishes the complete background of the project, outlines the stakeholder, and defines the specific scope taken up for our studio, forming the foundation for further work. Next, we focus on the concepts of level of development and level of schedule and how they guided our planning and modeling process throughout the studio. Level of development or LOD defines the accuracy, detail, and information maturity of model elements. The standard LOD progression includes LOD 100, 200, 300, and 400 for fabrication ready details. Level of schedule or LOS works alongside LOD by defining the structured sequencing of activities that support model development. Together, LOD and LOS form a unified framework that strengthens clarity, coordination, and decision making. The integration ensures that information evolves in a controlled manner, reducing rework and improving the reliability of both design outputs and project timelines. To implement these principles, we prepared a comprehensive weekly milestone design schedule similarly to what consultants develop in the real world projects. This schedule outlines when each discipline should complete their assigned activities. This approach helped us monitor progress, distribute responsibilities efficiently, and maintain accountability across all weeks. The schedule begins with foundational tasks such as BP and EIR preparation, followed by progressive discipline-wise LOD 300 modeling for structural, architectural, mechanical, electrical, plumbing, and firefighting systems. It then advances to resolution checks, model integration, LOD 400 development, quantity takeoff exercises, and eventually 4D and 5D simulations. This systematic sequencing ensures that every modeling stage is completed with the required level of detail before moving forward, reinforcing the importance of proper planning in BIM-based workflow. Further, the Model Element Authority table has been presented in this slide, which defines the responsibility distribution across all disciplines involved in the project. MEA essentially identifies who is responsible for creating, developing, and updating each model element, ensuring accountability and clarity throughout the BIM workflow. Based on our project scope, the architectural and structural models were developed up to LOD 400, which includes detailed reinforcement modeling and construction ready information. The MEPF services were modeled up to LOD 400, LOD 300, providing accurate system layouts and coordination geometry suitable for design and class resolution. This structured allocation of authorizationship helps streamline coordination, avoid scope overlaps, and strengthen interdisciplinary alignment. It supports efficient model development across phases, right from site development to architectural, structural, and MEPF systems. By clearly defining responsibilities, the MEA framework enhances clarity, reduces rework, and ensures that each discipline contributes precisely reliable data to the Federation BIM model. In this slide, the key model elements developed across architectural, structural, electrical, firefighting disciplines are showcased. Each component, from doors, walls, staircase, and curtain walls in the architectural scope of work to reinforcement, shear walls, and diaphragm walls in the structural scope, has been modeled with appropriate level of development to reflect accurate geometry and construction intent. Similarly, the electrical and firefighting systems, including cable trays, conduits, lighting fixtures, detectors, and pipe networks of various diameters, have been precisely represented to support coordination and systematic planning. All these models were created using Revit as a primary authorizing tool, ensuring consistency and accuracy in detailing. The entire workflow was supported through collaborative coordination on Autodesk Construction Cloud, enabling seamless communication among the stakeholders involved. This slide highlights the key elements developed under the mechanical and plumbing disciplines, each modeled up to LOD 300. The mechanical scope includes components such as exhaust ducts, air grills, butterfly valves, fresh air ducts, and chill water supply and return network. Similarly, the plumbing scope captures flushing water lines, solid soil and waste pipes, domestic water inlet pipes, and rainwater drainage systems. These elements have been modeled with accurate geometry and routing to support coordination with the architectural and structural models. The development of these systems follows the MEA Model Element Author Framework, which assigns clear authorizationship for every model element. This ensures accountability, avoids overlaps, and maintains discipline-wise clarity during model progression. This structured and collaborative workflow ensured that each service was modeled accurately and integrated efficiently within the overall BIM environment. Moving on with the LOD/LOS table, which outlines the week-wise progression of our design and modeling activities. It represents a section of overall design schedule that was originally developed in Microsoft Project. Each task has been mapped against the planned timeline, indicating when specific elements such as structural components, architectural elements, and initial setup activities were scheduled for completion. The table also integrates the MEA framework, clearly showing which discipline was responsible for which activity, ensuring accountability and smoother coordination throughout the design phase. By tracking the development of LOD 200, 300, and 400 models across multiple weeks, this schedule helped us maintain structured model progression, avoid delays, and align the entire team on priority tasks. Overall, this timeline served as a guiding tool to monitor progress and ensure that each milestone was achieved in accordance with the planned design workflow. Further, 4D and 5D simulations were developed for 22nd and 23rd floors, which formed the core scope of work of our simulation work. In simple terms, 4D simulation connects the 3D BIM model with the project schedule, allowing us to visualize the construction sequence over time. 5D simulation adds the cost dimension, enabling us to link quantities and rates with the model to generate accurate cost insights and earn value outputs. For the 4D workflow, the structural model with assigned pour IDs was imported into Navisworks and MSP schedule was linked to the model. Each activity was configured, animation settings were applied, and construction sequence was exported as the final 4D simulation. For a 5D process, quantities were extracted from Revit, unit rates were defined, and actual schedule from the LPS analysis were incorporated. These values were then transferred into Synchro to calculate actual quantities, cost, and generate earned value graphs. Both flows were divided into two pours, and these divisions helped us sequence the work accurately in the simulations. Overall, the integration of time and cost provided a clear data-driven workflow that strengthened forecasting, improved coordination, and supported better project control. This slide presents a staircase use case that we selected to study a practical constructability challenge and demonstrate how simulation can support better planning. On site, the staircase was not cast using the conventional single cycle approach. Instead, one portion of the staircase was casted together with the shear wall, and remaining portion was completed later alongside with the slab above. This non-traditional sequence created coordination challenges, making it an ideal case to analyze using 4D simulation. Through 4D simulation, we were able to visualize both the planned and actual construction sequence of the staircase, clearly identifying the activities that overlapped and the points where sequencing could be improved. By integrating these simulations, we could better understand how the sequence could be optimized to avoid delays, reduce rework, and streamline resource planning. The comparison between the model-based sequence and actual on-site staircase work highlights how digital workflows can help mitigate constructability issues and support more efficient decision making. Next, 5D simulation and on-value analysis for the 22nd and 23rd floor was done. The 5D simulation was developed both in Navisworks and Microsoft Project, where time and cost were integrated with the BIM model to understand not only the sequence of activities but also the financial impact of each stage. The model-based visuals shown here compare the planned versus actual construction activities, allowing us to identify deviations and monitor progress more effectively. Alongside this, an earned value analysis matrix was prepared calculating key performance indicators such as planned value, earned value, actual cost, cost variance, schedule variance, CPI, and SPI. These values were plotted on an S-curve, which provides a clear picture of the project's performance over time and highlights whether the work is ahead or behind schedule and budget. The 5D simulation also maps each task with its corresponding cost, helping forecast resource needs and supports more informed decision making. The QR code included on the slide allows direct access to the full 5D simulation, enabling viewers to observe the construction progression as per the actual timeline. Thus, summarizing the key learnings gathered throughout the study, beginning with the project brief, we developed a clear understanding of the scale, stakeholder roles, construction methodology, and on-site challenges associated with the commercial high-rise tower. Our studio scope was directly aligned with the real execution cycle and GFC release timeline, which allowed us to engage with the project in a realistic and industry-oriented manner. The integration of LOD and LOS was another major learning. It helped us understand how geometric detail and information maturity progress in parallel with design schedule, ensuring structured, accurate, and coordinated BIM development. The 4D simulation enhanced our ability to visualize construction sequence, identify workflow conflicts, and align planned activities with actual on-site operations. The 5D simulation further strengthened this by linking quantities, schedules, and costs, giving us a data-driven model for monitoring project performance and supporting informed decision making. Overall, the project provided a holistic experience in modeling, planning, coordination, and simulation, reflecting how BIM workflows operate in real-life project environments. Thank you for watching. Happy learning.